So when we have a regular HTTP invocation coming in, we're opening up a transaction, talking to some database. If we're unable to complete that transaction because, say, as we mentioned before, the server is under load, IIS decides to recycle our app domain, then that means that the database is kind of sitting there waiting for the transaction to complete, but it never does, right? So the connection is kind of left hanging. Eventually, the database will say, well, okay, I'm just going to roll that back if you're not going to complete it. And effectively, whatever data we tried to get into the database is not in the database. All of the memory that we had on this server, well, that's toast, right? And really, the data that came into our environment, it's not really anywhere, right? It's not on the web server. It's not in the database server. Really, the only place that it exists is somewhere out there on the client. But we've spent a very good number of years on the internet explaining to users, never click the submit button twice, right? And then we put all sorts of JavaScript on those pages to actively prevent them from clicking the submit button twice. So even if the data was there, it's not like we're going to be getting it from there. So data has effectively been lost. But the good news is that we haven't really left any evidence that that's actually happened. So if you're going to be committing a crime, at least be smart enough not to leave a lot of evidence behind you, right? So that's what's good about this type of scenario. Unfortunately, it doesn't work so well in the next scenario. So what happens when we get requests that are coming in? We try to go and talk to the database, but the database is down. Why might the database be down? Well, there's all of the regular physical reasons, but one of the most common causes for databases to be down is actually what happened here. Why is that? Because you see, when our server goes down, all of the connections that it had open to the database, as far as the database is concerned, it's still waiting for a response. So it doesn't roll back instantly. It only rolls back after a transaction timeout. Does anybody know what the default transaction timeout is for databases, not HTTP?
It's 30 seconds.
No, 30 seconds is the HTTP timeout, not the database timeout when dealing with transactions.
90 seconds.
What's that?
90 seconds.
90 seconds. You're heading in the right direction, not quite there yet.
5 minutes.
5 minutes. Good. Now we're talking minutes. That's a good step. It's 10 minutes by default. And again, you can configure this, but that's the default transaction timeout when you're doing data access against a SQL server. Why is it that long? Because a lot of times they're like, well, developers are writing fairly crappy code, right? I mean, people open up a transaction and they start just doing more and more and more stuff. And the problem is that if you time out ahead of that, then by the time that that code tries to commit to the transaction, the database will say the transaction is no longer in an enlistable state. And then the developer has to redo all of that work again. So that's why they default to very long timeout windows. Now the thing is, when you do that, the connection pool is left open for a very long time. So another app server tries to come in and get a connection to the database. The database says, sorry, my connection pool is full. Just totally utterly saturated because of that last server that went down and didn't clean up their connections. So you try to connect to the database, it says, sorry, connection refused. So you get an exception. What do you do with that exception? Log it, obviously. There's the first mistake. Do not leave evidence if you're going to be throwing away data. What do you do next? Tell the user, hey, something bad happened. Would you like to pick a different database to store your data in? I mean, it works for PowerPoint, right? So I tell you, hey, something bad happened. Please don't go away to our competitors. Try again. And the user clicks submit again, right? They kind of refresh their screen, they retype everything in. You do it really quickly. And then we try to connect to the database, and damn it, connection pool is still maxed out. Get another exception, write it to the log, tell the, hey, sorry, something bad happened. Please try again later. So once again, we're losing data from our system. because of this. It's still a transient problem, but it can be a very long time until this transient problem clears itself out. So let's talk about a less long transient period of time, deadlocks. So same scenario as before, valuable data coming into our system, us trying to get that data into the database. Need to write it to maybe 2 or 3 tables. We get some of that data into table number 1. We get some of that data into table number 2. The database is saying, oh, wait a minute, there's actually something else that's working on a lock on something that you're in the middle of working on. And eventually the database says, look, I don't see how I can have both of these transactions succeed. It tells you very nicely via an exception, your transaction has been chosen as the victim of a deadlock. Please try it again. Now, for those of you that are using NServiceBus, it will naturally catch that exception and retry, and then this thing will resolve itself. If you're doing this behind a web API and you get an exception, what's going to happen?
If you haven't implemented this strategy, then
Right. So if you don't implement the retry logic yourself, eventually that's going to throw and bubble up and come back to the user and say, well, you have some sort of 500 error, right? So once again, we'll write to the log, say we have designed the system in such a way that when it loses data, it makes sure to create lots of evidence of the fact that it's lost the data, right? That's Dexter 101, right? If you're going to do a crime, make sure you clean up after yourself, okay? And once again, tell the user, hey, there's a problem. So that's kind of the fundamental problem of traditional HTTP, TCP, RPC types of systems, is that when bad things happen at an infrastructure level, they are very susceptible to data loss. Now, this is one of those cases, again, going back to the whole RPC versus messaging comparison. When choosing infrastructure technology, one of the things that you want is something that is fairly reliable and also fast. To translate that to more everyday terms, you wouldn't be taking your loved ones, your family, etc., in a car that did not have airbags or seat belts or any of those other safety things. But the main feature is, but it goes really fast. So I'm not sure I want to drive really, really fast in something that unsafe. But that's the way that RPC works. It's really, really fast, but it's kind of unsafe around corners. Messaging, saying, oh, we're going to make sure that whatever bad stuff is happening around you, we've got airbags and all sorts of other safety mechanisms in place to make sure that nothing bad happens. And under those conditions, we'll go as fast as we possibly can, as fast as we safely can. And for most business systems, I'd argue that's probably a safer place to start from. So how does the queuing system, service busy type stuff work together? At a fundamental level, it's relatively simple. The first thing that happens when data is coming into our system, we write it into a queue. Now the thing is, most queuing systems actually provide an HTTP API to put data into the queue. So MSMQ, RabbitMQ, Azure Service Bus, the list goes on and on. You can invoke their API over HTTP. So you could have, whether it's a browser or a mobile device, effectively putting a message into a queue over HTTP, where until that ultimately gets stored successfully, the client doesn't get a confirmation. Now, the important distinction is that that is the only thing that happens. No processing happens at the time that the message is being put into the queue, which means we've really shortened the window down of something bad happening that can break that HTTP call. So really the question is, can I write the message to a queue? Can I write it to local disk? Not what is the status of the database, not what is the business logic doing. It really is the shortest, fastest possible operation. Assuming that that is successful, then everything else kicks into motion of pulling the message off of the queue, invoking your custom message handling logic, which then goes and talks to the database. There needs to be some sort of transaction mechanism here. I'm using the term DTC, the Distributed Transaction Coordinator, a little bit loosely. So if you're using NServiceBus with MSMQ and SQL Server, Oracle, etc., then distributed transactions are going to work out of the box, and this is going to be fine. If you're using, say, RabbitMQ, then RabbitMQ doesn't enlist into DTC. In NServiceBus, we have other features to give you a similar type of reliability behavior as distributed transactions would. So you don't have to worry about how all of that works right now. Fundamentally, when something goes bad, whether we're talking about this server crashing, the database being unavailable, etc., what effectively happens is that exception bubbles back, causes the message to roll back to the queue, and the database as well. Obviously, it's going to roll back eventually. But the important thing is that by default, data isn't lost. The message is still in the queue, and then can be effectively processed again. So this loop of saying, try to make that successful, pull a message off of the queue, doesn't work, try again, is something that is naturally built into almost every queuing environment. Because unless you tell the queue, that's it, that was successful, the message is going to roll back and appear there again.